Welcome to Organic Chemistry. In this video, we dive into nucleophilic substitution and elimination reactions. Let's get started. We begin by grounding ourselves in the fundamental distinction that underlies every substitution and elimination reaction: thermodynamics versus kinetics. Thermodynamics is obsessed with the free energy difference between the products and the reactants. And that is the Brønsted-Lowry world, the world of proton transfers, where acids and electrophiles in their definition actually converge. They mean the same thing. And bases and nucleophiles actually diverge in what those terms mean. Here, kinetics, by contrast to thermodynamics, asks how quickly can an electron pair be stabilized in a transition state. And this is, by distinction, the Lewis world, the world of electron pair transfers, where, again, nucleophiles and electrophiles are actually defined by the stability of that momentary high energy configuration. A little bit of contrast here is to take our electrophilic addition to an alkene. Those were enthalpy driven, and strong new sigma bonds formed with entropy decreasing. And so low temperatures favored addition reactions. Versus on the other side of that thermodynamic axis, elimination is the opposite. Entropy will increase and enthalpy is uphill. So higher temperatures will favor E1, E2 mechanisms. Now, the SN1 and the E1, the 1 in both of those terms, refer to the rate determining step, and that it is unimolecular. As you can see to the left, SN1 reactions begin with the slow unimolecular formation of a carbocation. Because the rate depends only on the substrate, the reaction only proceeds efficiently with a tertiary and some secondary carbons. Once the cation forms, everything else is fast. Fast rearrangements, nucleophilic attack, and ultimately you will have a racemization because the carbocation is planar. SN1 isn't regioselective or stereoselective, and of course it's prone to rearrangements. This is why SN1 and E1 are mostly pedagogical contrasts in modern organic synthesis. They are helpful to understand, but rarely desirable because of their poor selectivity. On the right, you can see E1 mirrors SN1 in its first step. That same slow carbocation formation. Once again, you'll only have tertiary carbons and some secondary carbons, the substrates that are viable. Here, the intermediate can lose a beta hydrogen to give an alkene. Because elimination increases entropy, E1 again is more favored than SN1 at higher temperatures. E1 is also partially regioselective, usually giving the more substituted alkene, but again, just like SN1, it suffers from rearrangements and lacks stereoselectivity. The real power of nucleophilic substitution begins here. SN2 is bimolecular. The nucleophile and substrate meet in a single synchronized step. The nucleophile approaches from the backside, and as it forms a partial bond, the leaving group departs in the same moment. It creates a sp3d trigonal bipyramidal like transitional state, planarized at the carbon, and always results in a Walden inversion. SN2 reactions are clean, predictable, and stereospecific. There are no rearrangements, there's strong regioselectivity, and there is total stereochemical inversion. We return to a bit of molecular orbital theory to help us understand the mechanism. In an SN2 mechanism, the transition state is delicate. A nucleophile must be able to approach directly behind the carbon leaving group bond. This geometric requirement means that primary carbons react most easily, secondary is slower, and tertiary carbons are essentially impossible. Bulky nucleophiles, or bulky substrates, will disrupt this geometry, blocking the approach and making SN2 inaccessible. So sterics, not stability, control SN2. And what makes SN2 possible at all is the constructive interference between the HOMO, highest occupied molecular orbital of the nucleophile, and the LUMO, the lowest unoccupied molecular orbital of the substrate, the sigma star anti-bonding orbital of the carbon leaving group bond. This makes a beautiful, almost musical picture of electron flow. The filled orbital donates amplitude into the anti-bonding orbital, weakening the carbon leaving group bond as the new bond forms. But this interference requires a clean overlap. Sterically hindered environments distort the lobes and shut the door, which is why tertiary substrates and bulky bases cannot perform SN2. Furthermore, allylic and vinylic reactivity will strongly differ. At a vinylic position, the sigma star carbon leaving group orbital is perpendicular to the pi system. This destroys the geometry necessary for backside overlap. Vinylic SN2 is impossible, but the allylic position is different. Because the sigma bond can rotate, the sigma star orbital can align parallel to the adjacent p orbitals. And this hyperconjugative alignment increases reactivity beyond even a typical primary carbon. This is one of the most subtle and beautiful SN2 insights. Orbital orientation matters even more than substitution. Now we enter the world of E2 mechanisms, the world of concerted elimination. The base removes a beta hydrogen at the same moment the leaving group departs. This requires that the CH bond and the C leaving group bond to be anti-periplanar, perfectly aligned but opposite in space. Because the reaction is bimolecular, we once again care about geometry and sterics. The product distribution is regioselective. Small bases will give the Zaitsev more substituted, more stable through hyperconjugation product. But the bulky bases will give the Hofmann less substituted product. To understand E2 mechanisms deeply, we again refer to molecular orbital theory. The base donates from its HOMO, highest occupied molecular orbital, into the LUMO, the sigma star orbital of the carbon leaving group bond. And that transfers electron density into that pi forming arrangement. For this to work, all the orbitals must be perfectly aligned in the anti-periplanar position. If the hydrogen and the leaving group are syn-periplanar, therefore misaligned, the reaction is impossible. So E2, like SN2, is fundamentally a orbital choreography. The electrons, lobes, and bonds must be moving in a beautifully synchronized movement. All this leads to the highlighting the stereochemical constraints of an anti-periplanar attack. Look at the left-hand side. We start with diastereomers. One is RR, the other SR. When each adopts the single conformation where the carbon, hydrogen, and carbon bromine bonds are anti-periplanar, E2 mechanisms can occur. If the RR isomer, in the RR isomer, that anti-periplanar arrangement places the two phenyl rings on the same side of the new double bond and gives us the Z alkene. In the SR isomer, the only allowable anti-periplanar arrangement puts the phenyl rings on opposite sides, giving us the E alkene. So E2 is most definitely stereospecific. Each stereoisomer of the starting bromide gives a specific alkene stereochemistry, determined entirely by the required anti-periplanar geometry. On the right-hand side of the panel, we have cyclohexane, and it's making an analogous point for ring systems. In cyclohexane, both the beta hydrogen and the leaving group must be axial in order to be anti-periplanar. If either is equatorial, there will be no E2 mechanism. A ring flip that places different beta hydrogens axial can lead to different regiochemical products, and bulky versus small bases will decide which of those axial hydrogens is actually abstracted. With a sense of the general SN2-E2 mechanisms, we now shift to reagents. But before assigning reagents to mechanisms, we need to reset our thermodynamic intuition. pKa is simply a measure of the equilibrium for proton transfer. And of course, equilibrium is governed by delta G. Strong acids live on the far end of this axis because their conjugate bases are exceptionally stable. Weak acids populate the middle, and extremely weak acids, like alkanes or amines, live on the far right. This entire axis is a thermodynamic one. Stable conjugate bases equal strong acids, and those stable conjugate bases make great leaving groups. So the deeper question underneath this slide is, what does stability look like? Resonance, electronegativity, size, and bond weakness. Once those principles settle in, the placement of every species on this chart becomes quite intuitive. And from that reference point, we now flip the lens. Bases, pKb, and leaving group ability. Leaving groups are excellent when the anion they form is stable. That's why iodide, bromide, chloride, and resonance stabilized anions dominate the left side of this axis. They are extremely weak bases. Their very weakness is what makes them so good at leaving. As we move rightward, we encounter increasingly strong bases, charge dense, unstable, and unwilling to depart. These species are excellent reagents, but terrible leaving groups. So the key idea here is good leaving groups are extremely weak bases. Bad leaving groups are strong bases. This slide again reinforces the thermodynamic backbone that all substitution and elimination chemistry stands on. And now we're ready to bring both thermodynamic and kinetic axes together. On the across the horizontal axis, we move from weak bases to the left to strong bases on the right. But across the vertical axis, we move from weak nucleophiles at the bottom to strong nucleophiles at the top. Starting at the top left, we have strong nucleophiles but weak bases. These are the best SN2 reagents. These are reagents that are linear, that are or planar, and highly polarizable. But they are weakly basic. And because they're not very basic, they don't grab beta hydrogens. So instead, they insert directly into the carbon leaving group bond and give a clean SN2 reaction. On the top right, however, we have the combination of strong nucleophile and strong base. These will exist in SN2 and E2 competition. With primary carbons, SN2 will most definitely dominate. But with tertiary carbons, of course, E2 will most definitely dominate since SN2 is impossible. This quadrant is where the mechanism will be sensitive to substrate structure, but also to reaction conditions. The bottom right, however, has strong bases but poor nucleophiles. These are your best E2 reagents. If the base is not bulky, it will give a Zaitsev product, the more substituted alkene product. However, bulky, charge-dense bases cannot approach the backside for SN2, but easily abstract beta hydrogens, and these will give the Hofmann products due to sterics. Finally, bottom left has weak nucleophiles and weak bases. These are inert reagents for both SN2 and E2, so they mostly represent excellent leaving groups, not reagents. Finally, we turn our attention to solvent effects, using either polar aprotic solvents or polar protic solvents. Solvents create the atmosphere in which electron transfer occurs. Here, polar aprotic solvents do something extraordinary. They do not hydrogen bond to anions. So nucleophiles remain completely exposed, not solvated, and energetically sharp, and therefore they are highly reactive. Here, SN2 is boosted dramatically. Meanwhile, polar protic solvents do hydrogen bond to anions, and they trap them in a thick solvent cage. This destroys nucleophilicity, completely suppressing SN2. But protic solvents also stabilize carbocations. So they enable SN1 and E1 when the substrate already favors that pathway. This slide makes the solvent logic explicit. Polar aprotic solvents will provide kinetic control and will typically be associated with SN2 and E2 mechanisms depending on the reagent. However, polar protic solvents provide thermodynamic control and will be completely associated with SN1, E1 mechanisms when they are the only reagent present. And although we introduce nucleophilic substitution and elimination reactions couched in the reactions associated with alkyl halides, really, as long as there is a good leaving group present, the logic of SN2 and E2 can be extended to a whole number of possible nucleophilic attacks and basic reactions. We end this video on focusing on water as a possible good leaving group. In contrast to this mechanism that we'll see on the following slide, recall the electrophilic addition of water that was acid catalyzed. In contrast to the acid-catalyzed addition of water, we can place alcohols in concentrated sulfuric acid with heat and dehydrate the alcohols. Dehydration of alcohols with a strong acid introduces a new element. Water becomes an excellent leaving group under protonation, and with heat, either E1 or E2 pathways are open to us. In concentrated sulfuric acid, water is so strongly hydrogen bonded that it effectively disappears from the reaction environment. This pushes the alcohol to shed water, a true dehydration. Tertiary alcohols undergo E1, secondary can show mixed E1, E2, primary tend towards E2. This closing slide shows unification of leaving group formation, reagent identity, solvation, temperature, and the patterns that converge to dictate the mechanism. Till next time,